Heisenberg Uncertainty Principle is one of a handful of ideas from quantum physics to expand into general pop culture. It says that you can never simultaneously know the exact position and the exact speed of an object, and shows up as a metaphor in everything from literary criticism to sports commentary. Uncertainty is often explained as a result of measurement, that the act of measuring an object's position changes its speed, or vice versa. The real origin is much deeper and more amazing. The uncertainty principle exists because everything in the universe behaves like both a particle and a wave at the same time. In quantum mechanics, the exact position and exact speed of an object have no meaning.
Now, I thought I would also introduce you to the uncertainty principle. This is the Heisenberg Uncertainty Principle, which is very easy to understand. However, these pop physicists such as, let's not state their names, but they're the ones that write all the books for the lay people to understand, try and make this so mysterious. And what they have invented, the word is spooky physics, and it's not spooky at all, because the Heisenberg principle is very rational. What it's saying is the approximate position of a particle is approximately times its velocity, or 1/2 Planck's time. So in order to understand the position of the particle, you're going to have to slow this down to 1/2 of Planck's time, which we know is a very small number, twice the speed of light. In fact, we have to slow it down in order to identify the position of the particle. But if you want to know the velocity of the particle, you're going to have to speed it up to double. So the trajectory, the velocity of a particle, is followed by a ghost line. But if you slow down the particle, you will never know which trajectory it's taking, because you've got to plot 3 points in order to get the absolute direction it might be going plus its speed. But if you want to know where the position of the particle is, you're going to have to slow that down. And once you slow it down and take a photograph of that single particle, such as a point on a magnetic plate, you don't know where that particle is heading because you haven't followed its trajectory, because we do not have the instruments that can measure both its position and its trajectory or velocity direction it's going at the same time, because we don't even have the ability to slow anything down below Planck's time or even below the speed of light. So we can only see ghost particles against a magnetic plate, and we can only see ghost tracks against a magnetic plate. We never see the particle or the wave or its velocity. And that's a very simple way of understanding it. It's not as spooky as they say. So I'm going to go down here and tell you that this explanation here is very vague and does not explain Heisenberg's uncertainty principle at all. In fact, it misses the point. It states the Heisenberg Uncertainty Principle states that you can never simultaneously know the exact position and the exact speed of an object. Why not? Because everything in the universe behaves like both a particle and a wave at the same time. Chad Orzel navigates this complex concept of quantum physics. Again, that is wrong. That is not what the uncertainty principle states. It just states we can't measure both the particle because it's slowed down too much, and once you slow it down, it loses its wave form, and then once you speed it up, it loses its particle form, because our measuring instruments cannot even measure either one of these. We only can measure the aftermath or the ghost tracking of both the particle and the wave, and we've got to do both separately, because if we're going to measure the position where that particle landed on the magnetic plate, we're not going to know which direction or how fast that particle is going, because in order to do that, we've got to speed it up, and then it loses its particle and becomes a wavy sine curve wave. That's my pop culture coming into my presentation. Anyway, I suppose you could call me a little bit paranoid about my revisiting quantum mechanics after approximately 10 years, but it's because there seems to be a vast change, or a subtle change, shall we say, in the way they're presenting the equations. And when I say they, I'm saying the new mathematicians and the new physicists who need to have something attached to their name, so they keep reinventing the wheel, but just writing its architecture in a different form with different formulas. So I wanted to discover again, revisit Planck's time, because I knew it was a very small number, and I pull up the Wikipedia and I see an equation I just don't recall seeing. And this is the equation, and I had to read further to understand what has happened. I'd never seen a C5 written 10 years ago. That just wasn't done. I'd seen C squared, I'd seen C quadratic, but never a C5. So I had to read this again, and what it says is Planck's time is sometimes defined in a reduced Planck's constant. So what they've done is they've just written the same Planck's constant and time dimension using a different formula, cutting it in half, in other words. So where they used h before, they're now using the h reduced Planck constant, which is half the Planck's time. So anyway, let's just go through. H equals h2. That's the reduced Planck constant. So I had to go back and re-look at the Planck's constant, and here was the equation I remembered. Reduced Planck constant is h over 2 pi equals 1054 times 10 to the 34th, because I had never seen a 44 in my life, and that's what this basically says it is it's a 44 here, and this is the reduced Planck's constant written. Anyway, let's just move on to the equation I remember, which always dealt with a 2 pi over h, and h equals 6.626 minus 34th, which if you understand that can also mean 6.666, like we say, the speed of light. And this 34, if you get rid of the 1, 0, that 34 becomes 66 times minus 33 joules per second. And then we get the 41, which is a constant there. But I'm just saying, I am remarking on the ridiculousness now of them writing Planck's time in this way, changing the traditional equations to a non-traditional. But again, I must say this is probably a more efficient way of writing it than the old way that they would do the equations, which is a longer equation. So again, I'm changing my mind right in the middle of doing my presentation. This is definitely a more compact way of writing Planck's time, but it does keep moving the ball for us old timers. So after I looked at this video all the way through, I do believe it's a very good explanation of the wave-particle duality, except that it does make it more complicated. So yes, we have to speed a particle down in order to measure where it lands, or we have to speed it up in order to measure its velocity. Now, this video does address a different aspect of the Heisenberg principle, which uncertainty principle is, yes, it is true. A particle at any given moment can be a wave or it can be a particle. It depends on when it collapses, and it collapses into a particle at, like I said, twice the speed of light, which we cannot measure, twice the reduced Planck, or it becomes a wave at the opposite end. So what you have is you have particles collapsing, beaming up, collapsing in, and then becoming a wave, and then collapsing, become a part. They breathe in and breathe out, breathe in and breathe out. In fact, they disappear and appear. They disappear and appear. They disappear and appear. They go into the Planck's dimension, which is the abyss, which we cannot measure. We can only measure after the abyss disappearance allows us to. So where it's going, how it's traveling, its trajectory, its velocity, which is momentum plus a direction, we have to speed it up in order to measure where the particle rested at any given point or became that wave collapse, that's when you slow it down. Okay, he's also touching on the fact that at any given moment, since we can't see anything faster than the speed of light, our measuring tools can't see anything faster than the speed of light. We don't know when that particle is going to be in its wave form or its particle form because, again, we don't have the measuring tools. So I like to address this as far as the standing wave equation goes. Basically, a standing wave is where a particle has both a position and a velocity of being in one location, where it does not go in a direction. It stays in its same location in space, still having velocity, but that's a looping velocity or the figure 8 velocity, and it loops in and out and over itself, and that is what a particle is. It is a standing wave form. So it's still a wave, but it's a particle because it's located at one location in space. So I like to liken this to the metaphor of the ocean. And oceans have waves that travel in and out and outward, spiraling inward, depending on the interference. That's called the Huygens principle of wave interference. But at some moment, you're going to have bubbles spark up, and those are considered the particles. It's the foam. It's the foam that always, if you could trap that wave at one point in its trajectory, one location in time, that foam would go all along the crest of the unseen wave that's underneath that foam, and you would not know the direction of the wave because it would be a snapshot in time. But once you start the camera again, and then the wave goes in a direction, and the little bubbles on top still stay on top of that wave, and they're moving with the wave, but for all intents and purposes, they're standing on top of that wave in one location, but that location is constantly moving on top of the wave. And that's what we call particles. That's why we have objects. That's why we have our bodies, because we are a collection of particles that are standing in one location at one particular time, at one particular location in space. And given the number of particles we have, yes, indeed, some of our particles disappear while other particles appear. And we just get the general gist of our bodies. Like I said in my previous video when I showed you the lemon, that lemon is mostly empty space. However, it stays in its location because it's being fed simultaneous equal waves, incoming and outgoing waves, which you recall Milo Wolf's interpretation of incoming and outgoing waves simultaneously having the same velocity and therefore canceling each other out at one location, and you got your wonderful lemon or your wonderful trees or your wonderful horizon line like Chicago, which I'm going to get into again. The flat earth keeps bringing me back to this flat earth theory, but that's what I had sat down to address this morning, and then I got caught up in this Heisenberg presentation, so I will probably address the flat earth in a different video.